you can almost guarantee that it won't work, not the first time out. So I think of the heart of the machine learning development process as error analysis, which, if you do it well, can tell you what's the most efficient use of your time in terms of what you should do to improve your learning algorithm's performance. Let's start with an example. Let me walk through an error analysis example using speech recognition. When I'm carrying out error analysis, this is pretty much what I would do myself in a spreadsheet. To get a handle on what are the errors of the speech system, you might listen to maybe 100 mislabeled examples from your dev set, from your development set. So let's say the first example was labels with the ground truth label, stir-fried lettuce recipe, but your learning algorithm's prediction was stir-fried lettuce recipe. If you have a couple of hypotheses for what are the major types of data in your dataset, maybe you think some of the data has car noise, some of the data has people noise, then you can build a spreadsheet, and I literally do this in a spreadsheet with a couple columns like this. And when you listen to this example, if this example has car noise in the background, you can then make a check mark or other annotation in your spreadsheet to indicate that this example had car noise. Then you listen to the second example. Maybe sweetened coffee got mistranscribed as Swedish coffee, and maybe this example had people noise in the background. And maybe one example with sail away song was mistranscribed as sew away song, and this again had people noise. And let's catch up was transcribed as let's catch up, and maybe this example had both car noise and people noise. Note that these tags up on top don't have to be mutually exclusive. During this process of error analysis, as you listen to audio clips, you may come up with ideas for additional tags. Let's say this fourth example had a very low bandwidth connection, and reflecting on the errors you're spotting, you remember, maybe quite a few of the audio clips have a low bandwidth connection. At this point, you may decide to add a new column to your spreadsheet with one more tag that says low bandwidth, and check that, and maybe go back to see if some of the other examples also had a low bandwidth connection. So even though I went through this example using a slide, when I'm doing error analysis myself, sometimes I'll literally fire up a spreadsheet program like Google Sheets or Excel, or on a Mac, the Numbers program, and do it like this in a spreadsheet. This process helps you understand what are the categories as denoted by tags that may be the source of more of the errors and thus may be worthy of further effort and attention. Until now, error analysis has typically been done via a manual process, say in a Jupyter notebook or tracking errors in a spreadsheet. I still sometimes do it that way, and if that's how you're doing it too, that's fine. But there are also emerging MLOps tools that are making this process easier for developers. For example, when my team Landing AI works on computer vision applications, the whole team now uses Landing Lens, which makes this much easier than a spreadsheet. You've heard me say that training a model is an iterative process, deploying a model is an iterative process. Maybe it should come as no surprise that error analysis is also an iterative process, where what a typical process would be is you might examine and tag some set of examples with an initial set of tags, such as car noise and people noise. And based on examining this initial set of examples, you may come back and say you want to propose some new tags. With the new tags, you can then go back to examine and tag even more examples. Let me step through a few other examples of what such tags could be. Take visual inspection. the problem of finding defects in smartphones. Some of the tags could be specific class labels, such as does this phone have a scratch or does it have a dent, and so on. So it's fine if some of these tags are associated with specific class labels Y. Or some of the tags could be image properties. Is this picture of the phone blurry? Is it against a dark background or light background? Is there an unwanted reflection in this picture? The tags could also come from other forms of metadata. What is the phone model? What is the factory? Which is the manufacturing line that captured this specific image? And the goal of this type of process, where you come up with tags, label more data, come up with tags, is to try to come up with a few categories where you could productively improve the algorithm. Such as, in our earlier speech example, deciding to work on speech with car noise in the background. Let me step through just one more example. Product recommendations for an online e-commerce site. You might look at what products a system is recommending to users and find the clearly incorrect or irrelevant recommendations and try to figure out if there are specific user demographics, such as, are we really bad at recommending products to younger women or to older men or to something else? Or are there specific product features or specific product categories where the recommendations are particularly poor? And by iteratively brainstorming and applying such tags, you can hopefully come up with a few ideas for categories of data that are worth trying to improve your algorithm's performance on. As you go through these different tags, here are some useful numbers to look at. First, what fraction of errors have that tag? For example, if you listen to 100 audio clips and find that 12% of them were labeled with the car noise tag, then that gives you a sense of how important is it to work on car noise. It tells you also that even if you fix all of the car noise issues, the performance may improve only by 12%, which is actually not bad. Or you can ask, of all the data with that tag, what fraction is misclassified? So far, we've only talked about tagging the mislabeled examples. For time efficiency, you might focus your attention on tagging the mislabeled and misclassified examples. But if there's a tag that you can apply to both correctly labeled and to mislabeled examples, then you can ask, of all the data with that tag, what fraction is misclassified? So for example, if you find that of all the data with car noise, 18% of it is mistranscribed, then that tells you that the performance on data with this type of tag has only a certain level of accuracy, and tells you that if it is mistranscribed, then that tells you that the performance on data with this type of tag has only a certain level of accuracy, and tells you how hard these examples with car noise really are. You might also ask what fraction of all the data has that tag. This tells you how important relative to your entire dataset are examples with that tag. So what fraction of your entire dataset has car noise? And then lastly, how much room for improvement is there on data with that tag? And one example that you've already seen for how to do this analysis is to measure human level performance on data with that tag. So by brainstorming different tags, you can segment your data into different categories. And then use questions like these to try to decide what to prioritize working on. Let's dive more deeply into an example of doing this in the next video. In the last video, you learned about brainstorming and tagging your data with different attributes. Let's see how you can use this to prioritize where to focus your attention. Here's the example we had previously with 4 tags and the accuracy of the algorithm, human level performance, and what's the gap. Between the current accuracy and human level performance. Rather than deciding to work on car noise because the gap to HLP is biggest, one other useful factor to look at is what's the percentage of data with that tag. Let's say that 60% of your data is clean speech, 4% is data with car noise, 30% has people noise, and 6% is low bandwidth audio. This tells us that if we could take clean speech and raise our accuracy from 94 to 95% on all the clean speech, then multiplying 1% with 60%, this tells us that if we could improve our performance on clean speech to human level performance, our overall speech system would be 0.6% more accurate, because we would do 1% better on 60% of the data. So this will raise average accuracy by 0.6%. On car noise, if we can improve the performance by 4% on 4% of the data, multiplying that out, that gives us a 0.16% improvement. And multiplying these out as well, we get 0.6% and, well, this is essentially 0%. Because we can't make that any better. And so, whereas previously we had said there's a lot of room for improvement in car noise, in this slightly richer analysis, we see that because people noise accounts for such a large fraction of the data, it may be more worthwhile to work on either people noise or maybe on clean speech, because there's actually larger potential for improvements in both of those than for speech with car noise. So to summarize, when prioritizing what to work on, you might decide on the most important categories to work on based on how much room for improvement there is, such as compared to human level performance or according to some baseline comparison. How frequently does that category appear? You could also take into account how easy it is to improve accuracy in that category. For example, if you have some ideas for how to improve the accuracy of speech with car noise, maybe with data augmentation, that might cause you to prioritize that category more highly than some other category where you just don't have as many ideas for how to improve the system. And then finally, how important it is to improve performance on that category. For example, you may decide that improving performance with car noise is especially important because when you're driving, you have a stronger desire to do search, especially search on maps and find addresses without needing to use your hands if your hands are supposed to be holding the steering wheel. There is no mathematical formula that will tell you what to work on. But by looking at these factors, I hope you'll be able to make more fruitful decisions. Once you've decided that there's a category or maybe a few categories where you want to improve the algorithm's performance, one fruitful approach is to consider adding data or improving the quality of that data for that one or maybe a small handful of categories. So for example, if you want to improve performance on speech with car noise, you might go out and collect more data with car noise. Or if you have a way of using data augmentation to get more data from that category, that would be another way to improve your algorithm's performance. One topic that we'll discuss next week is how to improve label accuracy or data quality. You learn more about this when we talk about the data phase of the machine learning project lifecycle. In machine learning, we always would like to have more data, but going out to collect more data generically can be very time-consuming and expensive. By carrying out an analysis like this, when you are then going through this iterative process of improving your learning algorithm, you can be much more focused in exactly what types of data you collect. Because if you decide to collect more data with car noise or maybe people noise, you can be much more specific in going out to collect more of just that data or using data augmentation without wasting time trying to collect more data from a low bandwidth cell phone connection. And this focus on improving your data on the tags that you have determined are most fruitful for you to work on, that can help you be much more efficient in how you improve your learning algorithm's performance. I found this type of error analysis procedure very useful for many of my projects, and I hope it will help you too in building production-ready machine learning systems. Next, one of the most common challenges we run into is skewed datasets. Let's go on to the next video to go through some techniques for managing skewed datasets. Datasets where the ratio of positive to negative examples is very far from 50-50 are called skewed datasets. Let's look at some special techniques for handling them. Let me start with a manufacturing example. If a manufacturing company makes smartphones, hopefully the vast majority of them are not defective. So if 99.7% have no defect and are labeled y equals 0, and only a small fraction is labeled y equals 1, then print 0, which is not a very impressive learning algorithm, will achieve 99.7% accuracy. Or medical diagnosis, which was the example we went through in an earlier video. If 99% of patients don't have a disease, then an algorithm that predicts no one ever has a disease will have 99% accuracy. Or speech recognition. If you're building a system for wake word detection, sometimes also called trigger word detection, these are systems that listen and see if you say a special word like Alexa or OK Google or Hey Siri. Most of the time, that special wake word or trigger word is not being spoken by anyone at that moment in time. So when I had built wake word detection systems, the datasets were actually quite skewed. One of the datasets I used had 96.7% negative examples and 3.3% positive examples. When you have a very skewed dataset like this, raw accuracy is not that useful a metric to look at, because print 0 can get very high accuracy. Instead, it's more useful to build something called a confusion matrix. A confusion matrix is a matrix where one axis is labeled with the actual label. So is the ground truth label y equals 0 or y equals 1, and whose other axis is labeled with the prediction. So was your learning algorithm's prediction y equals 0 or y equals 1? So if you're building a confusion matrix, you'd fill in with each of these 4 cells the total number of examples, say the number of examples in your dev set, in your development set, that fell into each of these 4 buckets. Let's say that 905 examples in your development set had a ground truth label of y equals 0, and your algorithm got it right. Then you might write 905 there. These examples are called true negatives because they were actually negative and your algorithm predicted it was negative. Next, let's fill in the true positives, which are the examples where the actual ground truth label is 1 and the prediction is 1. Maybe there are 68 of them. True positives. The false negatives are the examples where your algorithm thought it was negative, but it was wrong. The actual label is positive. So these are false negatives, so maybe there are 18 of that. And lastly, false positives are the ones where your algorithm thought it was positive, but that turned out to be false. So 9 false positives. The precision of a learning algorithm, if I sum up over the columns, 9, but let's fill in the true positives, which are the examples where the actual ground truth label is 1 and the prediction is 1. Maybe there are 68 of them. True positives. The false negatives are the examples where your algorithm thought it was negative, but it was wrong. The actual label is positive. So these are false negatives. So maybe there are 18 of that. And lastly, false positives are the ones where your algorithm thought it was positive, but that turned out to be false. So 9 false positives. The precision of a learning algorithm, if the are the ones where your algorithm thought it was positive, but that turned out to be false. So 9 false positives. The precision of a learning algorithm, if I sum precision of a learning algorithm, if I sum up over the columns, 905 plus 9 is 914, and 18 plus 68 is 86. So this is indeed a pretty skewed data set where out of 1,000 examples, there were 914 negative examples and just 86 positive examples. So 8.6% positive, 91.4% negative. The precision of your learning algorithm is defined as follows. It asks, of all the examples that the algorithm thought were positive examples, what fraction did it get right? So precision is defined as true positives divided by true positives plus false positives. In other words, it looks at this row. So of all the examples that your algorithm thought had a label of 1, which is 68 plus 9 of them, 68 of them were actually right. So the precision is 68 over 68 plus 9, which is 88.3%. In contrast, the recall asks, of all the examples that were actually positive, what fraction did your algorithm get right? So recall is defined as true positives divided by true positives plus false negatives, which in this case is 68 over 68 plus 18, which is 79.1%. And the metrics of precision and recall are more useful than raw accuracy when it comes to evaluating the performance of learning algorithms on very skewed data sets. Let's see what happens if your learning algorithm algorithm outputs 0 all the time. It turns out it won't do very well on recall. Taking this example of where we had 914 negative examples and 86 positive examples, if the algorithm outputs 0 all the time, this is what the confusion matrix would look like. 914 times it outputs 0 with a ground truth of 0, and 86 times it outputs 0 with a ground truth of 1. So precision is true positives divided by true positives plus false positives, which in this case turns out to be 0 over 0 plus 0, which is not defined. And unless your algorithm actually output no positive labels at all, you get some of the number that hopefully isn't 0 over 0. But more importantly, if you look at recall, which is true positives over true positives plus false negatives, this turns out to be 0 over 0 plus 86, which is 0%. And so the print 0 algorithm achieves 0% recall, which gives you an easy way to flag that this is not detecting any useful positive examples. And the learning algorithm with some precision, even as a high value of precision, is not that useful usually if its recall is so low. So the standard metrics when I look at when comparing different models on skewed datasets are precision and recall, where looking at these numbers helps you figure out, and of all the examples that are truly positive examples, what fraction did the algorithm manage to catch? Sometimes you have one model with a better recall and a different model with a better precision. So how do you compare two different models? There's a common way of combining precision and recall using this formula, which is called the F1 score. One intuition behind the F1 score is that you want an algorithm to do well on both precision and recall, and if it does worse on either precision or recall, that's pretty bad. And so F1 is a way of combining precision and recall that emphasizes whichever of P or R, precision or recall, is worse. In mathematics, this is technically called a harmonic mean between precision and recall, which is like taking an average but placing more emphasis on whichever is the lower number. So if you compute the F1 score of these two models, it turns out it to be 83.4% using the formula below here. And model 2 has a very bad recall, so its F1 score is actually quite low as well. And this lets us tell, maybe more clearly, that model 1 appears to be a superior model than model 2. For your application, you may have a different weighting between precision and recall, and so F1 isn't the only way to combine precision and recall. It's just one metric that's commonly used for many applications. Let me step through one more example where precision and recall is useful. So far, we've talked about a binary classification problem with skewed datasets. It turns out to also frequently be useful for multi-class classification problems. If you're detecting defects in smartphones, you may want to detect scratches on them or dents or pit marks. This is what it looks like if someone took a screwdriver and poked a cell phone. Or discoloration of the cell phone's LCD screen or other material. Maybe all 4 of these defects are actually quite rare, but you might want to develop an algorithm that can detect all 4 of them. One way to evaluate how your algorithm is doing on all 4 of these defects, each of which can be quite rare, would be to look at precision and recall of each of these 4 types of defects individually. In this example, the learning algorithm has 82.1% precision on finding scratches and 99.2% recall. You find in manufacturing that many factories will want high recall because you really don't want to let a phone go out that is defective. But if an algorithm has slightly lower precision, that's okay, because through a human re-examining the phone, they will hopefully figure out that the phone is actually okay. So many factories will emphasize high recall. And by combining precision and recall using F1 as follows, this gives you a single number evaluation metric for how well your algorithm is doing on the 4 different types of defects, and can also help you benchmark to human level performance and also prioritize what to work on next. So instead of accuracy on scratches, dents, pit marks, and discolorations, using F1 score can help you to prioritize the most fruitful type of defect to try to work on. And the reason we use F1 is because maybe all 4 defects are very rare, and so accuracy would be very high even if the algorithm was missing a lot of these defects. So I hope that these tools will help you both evaluate your algorithm as well as prioritize what to work on, both in problems with skewed datasets and for problems with multiple rare classes. Now, to wrap up this section on error analysis, there's one final concept I hope to go over with you, which is performance auditing. I found for many projects, this is a key step to make sure that your learning algorithm is working well enough, is what defects, and also prioritize what to work on. So emphasis on go out that is defective. But if an algorithm has slightly lower precision, that's okay, because through a human re-examining the phone, they will hopefully figure out that the phone is actually okay. So many factories will emphasize high recall. And by combining precision and recall using F1 as follows, this gives you a single number evaluation metric for how well your algorithm is doing on the 4 different types of defects, and can also help you benchmark to human level performance and also prioritize what to work on next. So instead of accuracy on scratches, dents, pit marks, and discolorations, using F1 score can help you to prioritize the most fruitful type of defect to try to work on. And the reason we use F1 is because maybe all 4 defects are very rare, and so accuracy would be very high even if the algorithm was missing a lot of these defects. So I hope that these tools will help you both evaluate your algorithm as well as prioritize what to work on, both in problems with skewed datasets and for problems with multiple rare classes. Now, to wrap up this section on error analysis, there's one final concept I hope to go over with you, which is performance auditing. I found for many projects, this is a key step to make sure that your learning algorithm is working well enough before you push it out to a production deployment. Let's take a look at performance auditing. Even when your learning algorithm is doing well on accuracy or F1 score or some appropriate metric, it's often worth one last performance audit before you push it to production. And this can sometimes save you from significant post-deployment problems. Let's take a look. You've seen this diagram before. After you've gone around this loop multiple times to develop a good learning algorithm, it's worthwhile auditing its performance one last time. Here's a framework for how you can double-check your system for accuracy, for fairness of bias, and for other possible problems. Step 1 is brainstorm the different ways the system might go wrong. For example, does the algorithm perform sufficiently well on different subsets of the data, such as individuals of a certain ethnicity or individuals of different genders? Or does the algorithm make certain errors, such as false positives or false negatives, which you might worry about in skewed datasets? Or how does it perform on certain rare and important classes? So the types of issues we talked about in the key challenges video earlier this week, any of them that concern you, you might include them in this list of brainstormed ways that the system might go wrong. For all the ways that you're worried about the system going wrong, you might then establish metrics to assess the performance of your algorithm against these issues. One very common design pattern you see is that you often be evaluating performance on slices of the data. So rather than evaluating performance on your entire data set, so you use one metric in this. Any of them that concern you, you might include them in this list of brainstormed ways that the system might handle data sets. False positive different genders, or does the algorithm make certain errors such as false positives or false negatives, which you might worry about in skewed data sets? Or how does it perform on certain rare and important classes? So the types of issues we talked about in the key challenges video earlier this week, any of them that concern you, you might include them in this list of brainstormed ways that the system might go wrong. For all the ways that you're worried about the system going wrong, you might then establish metrics to assess the performance of your algorithm against these issues. One very common design pattern you see is that you often be evaluating performance on slices of the data. So rather than evaluating performance on your entire depth set, you may be taking out all of the individuals of a certain ethnicity, or all the individuals of a certain gender, or all of the examples where there is a scratch defect on the smartphone. But to take a subset of the data, also called a slice of the data, to analyze performance on those slices in order to check against these things that may be problems. After establishing appropriate metrics, MLOps tools can also help trigger an automatic evaluation for each model to audit its performance. For instance, TensorFlow has a package for TensorFlow Model Analysis, or TFMA, that computes detailed metrics on new machine learning models on different slices of data. You learn more about this tool in the next course. And as part of this process, I would also advise you to get buy-in from the business or the product owner that these are the most appropriate set of problems to worry about and a reasonable set of metrics to assess against these possible problems. And if you do find a problem, then it is great that you discovered this problem before pushing your system to production, and you can then go back to update the system to address it before deploying a system that may cause problems downstream. Let's walk through this framework with an example. I'm going to use speech recognition again. If you built a speech recognition system, you might then brainstorm the ways the system might go wrong. So one thing I've looked at before for systems I worked on was accuracy on different genders and different ethnicities. For example, a speech system that does poorly on certain genders may be problematic, or also ethnicities. One type of analysis I've done before is to carry out analysis of our accuracy depending on the perceived accent of the speaker, because we want to understand if the speech system's performance was a huge function of the accent of the speaker. Or you might worry about the accuracy on different devices, because different devices may have different microphones, and so if you do much worse on one brand of cell phone, so that if there is a problem, you can proactively fix it. Or finally, this might not be an example you would have thought of, but prevalence of root mistranscriptions. Here's one example of something that actually happens to some of deep learning.ai's courses. One of our instructors, Lawrence Moroney, was talking about GANs, generative adversarial networks. But because the transcription system was mistranscribing GANs, because this unfortunately is not a common word in English language, and so the subtitles had a lot of references to gun and gang, which were mistranscriptions of what the instructor actually said, which is GAN. So it made it look like there was a lot of gun violence in that deep learning.ai course, and we actually had to go in to fix it because we didn't want that much gun gang violence in the subtitles. It turns out more generally, that mistranscribing someone's speech into a rude word or a swear word, that's perceived much more negatively than a more neutral mistranscription. And so I've built speech systems as well where we pay special attention to avoiding mistranscriptions that resulted in the speech system thinking someone said a swear word when maybe they didn't actually say that swear word. Based on this list of brainstorm ways that a speech system might go wrong, you can then establish metrics to assess performance against these issues on the appropriate slices of data. For example, you can measure the mean accuracy of the speech system for different genders and for different accents represented in the dataset, and also check for accuracy on different devices and check for offensive or rude words in the output. I find that the ways a system might go wrong turns out to be very problem dependent. Different industries, different tasks will have very different standards. And in fact, today, our standards in AI for what to consider an unacceptable level of bias, or what is fair and what is not fair, those standards are still continuing to evolve in AI and in many specific industries. So I would advise you to do a search for your industry to see what is acceptable and to keep current with standards of fairness and all of our growing awareness for how to make our systems more fair and less biased. One last tip. I find that rather than just one person trying to brainstorm what could go wrong, for high-stakes applications, if you can have a team or sometimes even external advisors help you brainstorm things that you want to watch out for, that can reduce the risk of you or your team being caught later by something that you hadn't thought of. I know that standards are still evolving for what we consider fair and sufficiently unbiased in many industries, but this is one of the topics that I think it'd be good for us to get ahead of and to proactively try to identify, measure against, and solve problems rather than deploy a system to be surprised much later by some unexpected consequences. So that's it for performance auditing. With this, I hope you have higher confidence in your learning algorithm when you go out to push it to production.